Welcome. The following is a presentation from Absolute Value Learning Center.
Okay, so today we'll solve this problem that I have posted on my website. It's called resistance in a conical wire. So let's read the problem first. Okay, it says a conductor of resistivity rho is machined into the shape of a truncated cone of circular cross section. One end has a radius A and the other has radius B. So this is radius A here and this is radius B here. The length of the cone is L. What is the resistance to the flow of current along its axis? Okay, so let's take a look at how to do this. Before we get started, a little bit of background on resistance in a conductor. So for a conductor of length L and which has uniform cross section A and resistivity rho, the resistance is given by R equals rho L over A. Okay, it makes sense because the resistance is proportional to its resistivity, it's proportional to how long it is, and it is inversely proportional to the area. That means if the area is higher, then its resistance is lower. Okay, just like water flowing in a pipe. If the area of the pipe is higher, then more water can flow, right? Faster. So however, in our problem, the cross-sectional area A is not uniform, right? It kind of tapers to one end. It is a function of the radius r at any given point, of course. Like here, it's a function of radius r, but r is a function of x. Okay, r varies along the x-axis. So what should we do? So this picture kind of gives you some clue on what we can do, but let's take a deeper dive. Okay, so what we do is we take a narrow length of narrow wire of length dx, right? And dx is situated at x, at a distance x from one end, and we assume that across this small length dx, the radius of the wire doesn't change much. Okay, so it is r here and r on this side, so the radius doesn't change. So then we say, okay, if the radius is constant, then the cross-sectional area is constant, so along that little length of wire, our radius should be constant, and therefore we should be able to use the formula for resistance that we had earlier. So we can just say that across that little length dx, the little resistance dr is rho dx over ax, right? This business of setting up such an equation is called setting up a differential equation, right? So we set up a differential equation. This is a classic technique in physics, and this is how calculus comes into physics, and you'll see this repeatedly, that math pretty much is the language in which physics is spoken, okay? So dr, that small little increment in resistance, is rho dx over ax, where a of x is pi times r of x squared, where r of x is the radius at some distance x. Okay. So, but what is rx? How do we relate the radius at any point x to x itself, right? How do you do that? So again, we will need to go into some math here, okay, some basic coordinate geometry and straight lines in order to understand the relationship between the radius at some x and x itself, okay. So let's see how we do that. So here I have a graph, representing r of x on the y-axis and uppercase X along the x-axis, and here is the top edge of our conical wire, okay. Now this is a straight line with 2 points known to us. So this point here is 0, a, right? And the other point is L, the distance is L, the whole length of the wire is L, and the height here is B, so L, B. So we know 2 points on a given straight line. So if we have any running point x, Rx on the straight line, we can find out what is the relationship between R of x and x, right? We use a 2-point formula. So what does the 2-point formula say? It says that if you know 2 points of any given straight line, then the slope between this point and this point should be the same as the slope between this point and this point. Any 2 points you take the slope, it should be the same. That would be the slope of the straight line, because the property of a straight line is its slope is constant, right? So let's do this. Let's take this point and find what the slope is. The slope is, of course, y2 minus y1 over x2 minus x1. So rx minus a over x minus 0. And similarly, b minus a over L minus 0 if you take these 2 points, b minus a over L minus 0. The two should be equal. So that gives us a quick equation. L times Rx minus a should equal b minus a times x. So R of x is b minus a over L x plus a. So we have a relationship between R of x and x. which we can plug into our relationship for area to get how area depends upon x. Okay, and this is the function we were looking for, how area depends on x. So that a of x will now we should be able to plug that into this differential equation we had set up earlier and solve the differential equation. Now, how do you solve the differential equation? Of course, you take integrals on both sides. So you take the integral on the left hand side of dr, then the limits are from 0 to r. And why is that? Because the resistance is 0 here on one end of the conical wire and it's r at the other end. Okay, so 0 to r dr, which is just r, is equal to the integral 0 to L of rho dx over ax. So you plug in the value for ax, then what happens is the rho over pi drops out as a constant, and you have dx over this squared. How do you solve this? So you make a substitution. You say let u equal b minus a over L x plus a. Then d of u, of course, is just b minus a over L dx. And you plug these two values. You plug the value of u in here, so this is u squared. And then you plug the value of dx from here. Dx is du times L over b minus a. So you get du times L over b minus a, and L over b minus a is also a constant. So that drops out of the integral. All you're left with is integral of du over u squared. Now you have to be careful about the limits. Okay, when x is equal to 0, then what is u? And when x is equal to 0, u is equal to a. So that's what happens here. And what happens when x equals L? When x is equal to L, the two L's cancel out and you get b minus a plus a, which is b. So the limits of our integration change, okay, as you make that substitution. So what is du over u squared integral? It's just minus 1 over u. So you plug in minus 1 over u and you go from b to a, so it's minus 1 over b minus 1 over a. So that's where the plus comes in here. And if you do some simple algebra here, you get rho L over pi AB. Now let's make sure this makes sense, right? So normally you would have rho L over pi A squared if the cross section was A everywhere, right? If the radius was constant and it was A, you would get rho L over pi times A times A. But now you have A times B. So at least dimensionally this makes sense, okay? L over some L squared, right? But this resistance is A times B and B is smaller than A. So that means this resistance is higher. Does that make sense? And it does. Because if the area was constant, then the resistance would be lower than if it is tapering. Now because it's tapering, the resistance at this end is higher because resistance goes up as area goes down. So therefore, we expect that in a conical wire, the resistance will be higher than if the radius was constant all through. Make sense? All right, so that's our answer. Thank you.
We hope you enjoyed this presentation from Absolute Value Learning Center. Please follow us on Instagram at absolute.value.learning and go to our website to register for courses today. Thank you.